Thank you for joining this webinar today. So my name is Philippe Lebleu. I'm the mining manager for AMC Mining Consultants in Vancouver. Just a bit about myself. I have about 20 years experience split between operational work in Malaysia, Australia, Brazil, and Canada. And I've got quite a bit of experience as a consultant in various countries as well. So today I'm going to talk to you about modern open pit mine planning. And I will describe 3 types of software that we use over the past few years and some more recently, and show you how these tools can be used together with the right expertise to improve the mine planning process and the value generated at your mine or project. So if you look at your screen, you'll be able to see that you've got a chat option. Please feel free to type any questions, and I'll try to answer like 3 to 4 at the end of the presentation. So first, I'm going to talk to you about strategic optimizers, which are software that are used for strategic, long-term, and life-of-mine planning. That's going to be based on 3 case studies at operating mines. We will then look at an example of direct block scheduling, which is an alternative to the Lurch-Grossman algorithm for pit optimization and pushback definition. And finally, we'll look at interactive pit design and how software are automating the pit design process. So when I talk about strategic optimizers, I'm talking about commercially available software. So for example, at AMC, we use MineMax Scheduler. But just be aware that not all software were created equal, and not all strategic optimizers offer all the capabilities that I'm describing in this presentation. So what's strategic optimization? So to me, strategic optimization is the definition, is a derivation of the most attractive mine development plan that achieves the company's corporate goals within the limits of practical constraints. And I will emphasize practical because there's no point in deriving a so-called optimum solution if it cannot be readily implemented in the field by the operations team. So typically, strategic optimization involves solving complex problems governed by multiple variables and constraints, which often conflict with each other. And I've listed a few here. So you've got the deposit geometry and its associated grade distribution and strip ratio, geometallurgical parameters, which dictate recoveries and throughput rates for different material types. You've got operational constraints, which impact on the sequencing and the rate of advance of pushback. Environmental constraints, which can dictate, for example, your waste dumping strategy. You've got product grade specification, cost and revenue for different material types, and processing and material handling methods. So to deal with those complex issues, engineers have, at least in the past, reverted to oversimplifying the problems, and very often to using a sequential approach, as is shown here on the left-hand side. So with that more traditional approach, cutoff grades and ore destination are predetermined before scheduling, and that obviously doesn't provide a lot of flexibility during the elaboration of the mine plan. After a schedule is produced, often one period at a time, waste dumps are designed and equipment numbers calculated. And then this process is repeated again and again until a satisfactory solution is found and a final schedule is selected. One of the issues with using older generation strategic software lies in the fact that schedules are derived on a period-by-period basis, without being able to readily evaluate the impacts of a decision taken in the first year, for example, on subsequent years or even the entirety of the life of mine. So as opposed to solving our complex mining problems by following a sequential approach, strategic optimizers allow mining engineers to look at a multitude of variables and constraints at the same time in order to maximize the overall project value. And that project value can be anything that your company is looking for, such as, minimizing capex, minimizing paybacks, and so on. And we will look at this in more details when I go through the 3 of the case studies. But as you can see on this diagram, strategic optimizers allow to simultaneously look at sequencing of your pushback based on operational constraints and our presentation, applying variable cutoff grades on a period-by-period basis, especially if you're trying to come up with a stockpiling strategy and you're trying to follow a high grading strategy. Dispatching all to different plants to maximize the value of the project. Adhering to blending and grade specifications. Optimizing the waste dumping sequence and the waste dump shapes. And all of that while respecting equipment utilization and constraints. One of the added benefit of this software is that capital expenditure injection decisions can be made on the go. So for example, this software can decide when to expand a processing plant, relocate an in-pit crusher, for example, or add additional haul trucks to achieve the desired objective. And all of that can be done thanks to their look-ahead capability. So I'm going to describe our first case study, which is based on cutoff grade and stockpile optimization. So the goal here was to rapidly determine with a strategic optimizer whether an elevated cutoff grade strategy was more beneficial to the mine rather than feeding the plant with a more constant grade profile. So the example here is of a gold mine which was processing oxide, transition, and fresh ore, which each of those materials had a variable throughput rate, recovery, and cost. So to look at those two different scenarios, the method we used was to define 4 high-grade bins, which were derived by analyzing the deposit's grade distribution. Material from these grade bins could either go directly into the plant, or they could be sent to a high-grade or low-grade stockpile. So here we kept the number of stockpiles low to take into account practicality and the limited stockpiling area available on site. And because we were dealing with variable throughput rates, the strategic optimizer was set up to maximize value by being constrained by annual planned operating hours, as opposed to mill feed tonnage in a more traditional case. And the 3 graphs here show you the results of the 2 scenarios. So the top left-hand side shows you the mill feed grade for the 2 scenarios. The high grade being shown in purple, and the no high grading or constant mill feed shown in green. So as you can see on that first graph, by following a high grading strategy, we're able to produce a higher grade during the first years of operation. If you look at the total material movement ex-pit, you can obviously see that to get those higher grades, we had to move additional material in the first years of production, raising total material movement to about 60 million tons per annum for the first 4 years. And obviously, if you look at the last graph, moving additional material at the start of the mine life required bringing forward some of the capital expenditure for purchasing mining equipment. But overall, the high grading strategy resulted in an increase of $30 million in NPV, increased the IRR by 3%, and increased the payback period by about 1 year. I think that what's important here as well is to be able to demonstrate the incremental value of your different scenarios, because even if a strategic optimizer provides the optimum solution for a specific scenario, it cannot yet take into account some of the softer issues or risk that would negate any marginal financial benefits of any of your respective scenarios. So I think it's really important to be able to provide all the ammunitions to the decision takers, so they can globally decide on what strategy is the best to adapt to your site. So in our second case study, we're looking at blending and multiple plants. And here we've used strategic optimizers to help us with difficult blending scenarios and having to feed ore to multiple plants at the same time. So we were looking at an iron ore operation with two deposits, like pit 1 and pit 2. And the goal here was to optimize NPV while producing 2 products to grade specification and postpone the operation of a washing plant or beneficiation plant for as long as possible. The main challenge here was that we were dealing with 10 contaminant constraints, and as you can see it on the graphs on the right-hand side, the contaminant distribution was very high, very variable, and on a pit by pit and bench by bench basis. And on top of that, all could be fed to 3 different plants. So, for example, material from pit 1 could go to a stockpile. It could also go to a direct ship ore plant or DSO. It could also go to a beneficiation plant where the ore could be washed. So you'd lose about 20% of the material, but on the other hand, you then get like much cleaner product with less contaminants. Material for pit 2 could go to a stockpile or could go to its own direct ship ore plant, or go to the same beneficiation plant as for material from pit 1. And all of the material would then make its way to the train loadout facility. What was interesting as well is because of the total capacity of the individual plants was higher than that of the train loading capacity, an almost infinite number of combinations of plant feed could be used to load the trains with the required tonnage. So, for example, you could send 80% of the material to the DSO plants and only 20% to the beneficiation plant, or 70% to the DSO and 30% to the beneficiation plants. So you can see that there were far too many combinations of plant mix and mining sequence to optimize the schedule using a traditional approach and produce within grade specifications. So in this case, the strategic optimizer allowed us to postpone the operation of the beneficiation plant by 9 months without impact on the life of mine. And as you can see on those graphs, that was done by widely fluctuating the contaminants coming from pit 1 and 2, as shown in the by the gray and the black lines, to be able to produce the contaminants below the specification. So this example demonstrates how strategic optimizers can be used to your benefit to automatically allocate ore to multiple plants or to deal with difficult grade specifications. So I talked about iron ore, but that could be equally applicable to like a copper deposit, for example, where you've got a high arsenic content, or to a gold mine where you're having to dispatch ore to a heap leach or a CIL plant. In our last case study, we were looking at waste dump optimization. So what we were tasked to do was to compare the benefits of in-pit dumping against out-of-pit dumping while producing a constant ounce profile for a gold mine in Africa. So to do that, we designed a maximum dumping envelope for the out-of-pit dumps, and that can be seen in the top left-hand side graph, pretty much the black shapes subdivided into blocks. What we also did was to design in-pit dumps for each relevant phase that could safely be dumped onto while mining adjacent pushbacks. We also designed all potential haul roads from each pushback to each destination. And then we set up the strategic optimizer so that one block of waste was given the choice to go to any dumping location, in pit or out of pit. And for each of the out of pit dumps, we had up to like three ramps. And you can see in the top left-hand side corner how that's translated in the brain, if you're on the strategic optimizer. So you get the decision tree, and that really shows that like how the optimizer would decide where to send the waste block. So then, by calculating cycle times to each destination, calculating truck hours, and using truck capex as an input, we're able to optimize the NPV and compare the two different scenarios and produce an optimized mining and dumping sequence at the same time. And you can see the result of the in-pit scenario on the right-hand side. So in red, you can see the shape of the final in-pit dumps, and in purple, you can see how the strategic optimizer populated the maximum dumping envelope. So overall, the trade-off study showed that an additional $15 million in NPV could be generated by following the in-pit dumping strategy. And obviously, I was talking previously about software issues and risk. We had to evaluate whether the gain in NPV was worth the potential sterilization of ore below the in-pit dumps. And in this case, it was worth it. So the in-pit dumping strategy was followed by the mine on site. So in more complex scenarios, strategic optimizers can be used to determine the best mining sequence. If you're dealing with acid generating waste, for example, that needs to be encapsulated by inert waste on site, or in scenarios where mining is to be accelerated in certain pits to provide storage for tailings inside the pit void. So moving from the strategic optimizer into direct block scheduling. So as you know, the Lurch-Grossman algorithm, which is widely used in pit optimization, allows you to obtain an optimized pit shape based on undiscounted cash flow. The problem is that it does not necessarily take into account other constraints that you will have to consider when producing a mine plan. And an important one that we talked about is blending. So I think that it's important that you ask yourself whether if you are able to incorporate a series of scheduling constraints at the pit optimization stage, would that produce a more optimal pushback shape and final pit optimization? I think the question is yes, especially if you're dealing with a very complex mining setup. So direct block scheduling allows you to integrate the pit optimization process with some aspects of strategic scheduling to define pushback shapes, optimized not only on value, but also on honoring a multitude of scheduling constraints. And we can see that in the that example of a copper mine with a high arsenic content. So because of that high arsenic content, it meant that ore had to be blended to meet grade specifications. So if you look at the, I'll describe the two methods. So the more typical Lurch-Grossman based method with the graph shown on the at the top, and a method following the direct block scheduling, or DBS, with the graph shown at the bottom. So by following a more traditional approach and using the Lurch-Grossman pit optimization, we're able to define pushbacks based on value, and you can see that in the top left-hand side picture. Obviously, we couldn't use the high arsenic constraint to better define pushbacks, but we did some manual analysis to understand the arsenic distribution, and by playing around with cutoff grades and so on, we're able to optimize those pushbacks a bit. We then inputted the pushback into a strategic optimizers and run a schedule. Obviously, when we run the schedule, we then apply the arsenic constraint. When we followed the DBS method, we first optimize just based on value, and you can see in the bottom left-hand side graph that the ultimate shape of the optimization is very similar to the one obtained with the Lurch-Grossman method. Just note one thing, so whether in the Lurch-Grossman method you're seeing pushback shapes depicted by the different colors, with the DBS method you're only seeing the period mined. Then what we did, we actually incorporated that high arsenic constraint, and you can see how the DBS, the colors of the DBS started to change. So that meant that the pushback shape changed, and the mining period also changed. We then used the results of the DBS to define pushbacks and incorporated that into a strategic optimizer. So by using the same process with the strategic optimizers, we were able to really obtain a like-for-like comparison, if you want. And here we increased the NPV by about $17 million using the DBS method. So I think that this example shows you like the potential of better defining pushbacks using advanced optimization tools, especially when you're dealing with complex mining settings. So moving on to interactive pit designs. So if you've designed pit designs in the past, you know how time-consuming and manual the process can be. So I'm sure that everyone would have an example of spending an hour on projecting and expanding your strings bench by bench, only to realize at the end that your ramp is located under the crusher and having to start again. Improvement in design packages are now allowing you to rapidly and interactively evaluate the placement of ramps and switchbacks and see pit walls move instantaneously based on your decision. So you can see this in the example at the bottom. I don't think it's working, so I'll play it again after. But so pretty much what we've evaluated is that with some of those design packages, they allow you to produce a design in a fraction of the time compared to the more manual editing process. So that's great, but I think that more importantly, this software allows you for rapid evaluation of multiple designs that can be evaluated in your strategic optimizers to really be able to evaluate the impact of your design decisions on your schedule. Because obviously sometimes when you do design modifications, that will impact on the way you can actually design, schedule your phases. So in conclusion, I would highly recommend the use of a strategic optimizer in your next project or at your operation. I think that their proper use regularly results in increasing value of 10 to 20%, especially if you're dealing with a complex mining setup. Direct block scheduling seems to be like one of the promising advances in software development that will help define better pushback shapes based on a battery of scheduling constraints. And as I'll show you like later on, interactive design tools are helping to automate a traditionally very manual process. Finally, I think that it's essential that you produce just one optimum scenario, but you produce a few to be able to tell the story as to why a specific option has been selected by demonstrating its relative value against that of other options. That way, decision makers can make an informed decision based on all influencing parameters, which encompass more than just cash flow. And finally, no matter how sophisticated the mining software have become, it is really important to still place experience and practicality at the center of the mine planning process to ensure that it's practical and achievable in the field. Thank you.